Hi everyone, welcome to ECON 483. In this first lecture, I'm going to go over an introduction. In particular, I will talk about linear models, so that should be a flashback from ECON 333 and maybe other econometrics courses you might have taken. I will talk about different distinctions between random variables. I will talk about terms like consistency. I will talk about some definitions about what machine learning is, expectation, variance, and then I will talk about linear models in detail. First, I want to start this lecture by saying that I do not legally allow this content to be published without my consent. If I see this content being uploaded on another platform than Canvas here, I will take the content down and I will report the name of whoever posted that content. So in this first slide, I want to give you a course overview. In this course, we are interested in the following model. We have a variable yi. Note that it is uppercase because it refers to a random variable. I will get into this in a bit. Where this variable yi, so observation y for individual I, is equal to a function f of a set of variables x, which we are going to call covariates. So they each correspond to observation I, so to the observation of individual I, and we have variable x1, variable x2, all the way to variable xk. Okay. Finally, we have a last term, epsilon I, which is a error term or a disturbance term. It is in general the leftover. It is like the whatever is not explained by the main functional form. So y is the outcome variable. So where I am going to use different names over the course is going to be either outcome variable, explained variable, or dependent variable. It is the explained variable because I want to explain it by this function of the x's. I'm going to call it as well dependent variable because it depends on the x's. Or in general, it's also dubbed the outcome variable. Epsilon I is a random disturbance, also called the error term. Again, there are different ways to call the same term because here we are at the intersection of econometrics, statistics, and computing science. The machine learning aspect here is at the intersection of those three different fields that each have a specific jargon for all these terms. The x's are what are called the explanatory variables because they have the explanatory power, or the independent variables if you oppose them to y, which is the dependent variable. We also call them the covariates or the predictors. Why? Because at the end of the day, we will be focused on predicting the variable y given some observations x. So my observations x will help me predict the variable y. I mentioned that y and x are in uppercase form, which means that they are random variables. We observe realizations of them in the data. So when it's a realization, I will be using lowercase letters, small y and small x. Epsilon is also random, but in the literature, it's commonly accepted to use the term epsilon for an error term without having to use the uppercase form. So this is the overall overview of the course. Now, depending on what kind of problem we are interested in, f might take a specific form or f might take no form, but in general, we are interested in estimating this relationship between y and the x's. So we want to know more about f. Sometimes we will assume the shape that f takes, like a linear model, for instance. Why not? It could be any other functional form. Or Other times, we will stay agnostic about what f is. We say, oh, f is some relationship. It could be a weird cycle function, it would be a weird curve, anything, but it doesn't matter. What matters is, at the end of the day, we want to get accurate predictions. This equation, equation 1, is called the population regression equation. I say population here because it doesn't contain anything which is related to a sample yet. It is the true relationship that holds, and we are going to use this as our baseline assumption when we look at actual data. So here is the outline of the lecture. I will start by talking about definitions and notation, which I will use throughout the course, which you will have to employ as well once you present some papers later in the semester. I will define what an estimator is and why we are interested in estimators. What kind of estimators are we interested in? So I will focus on some particular properties which are statistically appealing. Then I'll get into the linear model. This will be close to what you've done in ECON 333 and other econometrics courses. So as a consequence, I'll talk about the OLS estimator, the ordinary least squares estimator. I will define it again, show its properties, talk about its properties. And I'll talk about things around the OLS estimation. I'll talk about the goodness of fit. You might remember something called the R squared. I will talk about that. And I will talk about inference and hypothesis testing. Finally, I will show how the OLS estimator can be implemented in R. I will show you a bit of code with some graphs. I will comment on this. So if you want, once we get into the illustration in R, you can have a laptop with R as well on the side with my code, run the code at the same time to see how things are going. I strongly suggest you to do that because learning how to use statistical software by watching somebody put comments is, one, incredibly boring, and two, not very efficient when it comes to learning. A language is something you learn by practice, so you need to practice. First, the best way to practice is to get some of my code, copy, paste it, change a couple things. You can submit a comment or something in the chat and say, oh, if I put this command, it doesn't work. We can talk about that. And this way, lecture after lecture, you will gain a hopefully some kind of a foundation for R if you don't already have such a knowledge. Any questions before I get into the appetizer? Good. Let's move on. Ooh, I forgot to mention, sorry, that for this lecture, I suggest you guys read chapters 1 to 3 in Introduction to Statistical Learning with R. They are suggested, not required. I will pretty much talk about the same thing. The book might have a couple more things that I will show, but I will also show things that are different from the book. The overall knowledge is pretty much the same, so take the book as a complement if there is something in the slides that you don't understand. I might make shortcuts sometimes. Maybe sometimes I'll assume that there is something you already know and that you might not know. You can ask me during the lectures or in office hours. And you can always look at the book if you want to see another formulation of the same terms. Sometimes this helps a lot. I try to follow the notation of this book as closely as possible in this lecture, and I believe in the remainder of in the other lectures as well. Okay, so let's get the appetizer. Let's get some definitions and some notation. First of all, in this course, we will distinguish estimation problems and prediction problems. At the end of the day, the whole course is about estimating this function f that I talked about before. Note that now I use x here I use the lowercase x here to say that x are variables I observe, and I want to estimate f when I observe those numbers to predict the corresponding y of observation I. Now, what assumptions to make or tools to use depend on whether one wants to estimate or predict. In general, they go hand in hand, but there is a distinction that is going to call for one statistical method over another. And that will get us into for which kind of problems we use machine learning. Estimation is about learning about a specific parameter of interest. Estimation problems make assumptions about the nature of the function f in one. I will get into the linear model later, but I can give you a taster already. If you assume that f is linear, then you get to the linear model where y is equal to xi times beta 0 or beta 1 or something. Once you make this assumption, what you want to do is estimate beta and obtain an estimate beta hat. That will help you do two things: estimate the marginal impact of x on y and marginally predict y. But if I only care about prediction, I only care about predicting the variable y. So if it's just about guessing or predicting the value of the dependent variable for some values of the covariates, then I only care about making accurate predictions of the function f. I don't necessarily need to assume a specific functional form. After all, assuming a specific functional form is a big assumption, and it might be an inaccurate assumption. So every time you make assumptions when it comes to statistics, you need to know what you can get with it, what are the advantages of making this assumption, but also what are you sacrificing, what are you losing. In this course, we will focus on both estimation and prediction, but I will just every time let you know what kind of method is more or less used for what kind of problem. So, this course is called Machine Learning in Economics, and hopefully I won't sell myself short. So let me give you a definition of machine learning here, although I won't talk about it for the rest of the lecture today. First of all, there are many definitions that differ on different aspects. So I got two different definitions, one of them from, of course, Wikipedia, but I checked the definition and it's pretty good. So I confirm that this is one of the possible definitions for machine learning. It is the study of computer algorithms that improve automatically through experience. It is seen as a part of artificial intelligence. Machine learning algorithms build a model based on sample data, known as training data, in order to make predictions or decisions without being explicitly programmed to do so. Couple of things to unpack from this definition. First of all, computer algorithms. An algorithm is a sequence of instruction that the computer is going to execute. In general, the computer is going to execute them in a repetitive or an iterated fashion. And I'll talk about loops a bit later once we get there. So it's an algorithm, so it's a sequence of instructions that improve automatically through experience. The word automatic means that we need to write the code the first time, but once it's written, hopefully it will improve on its own every time you feed it new data. That's the idea. And what I mean by feed new data is what experience means. Every time you make your algorithm go through some of your data, we say it's called machine learning if it improves one way or another with time, with the number of experiences. In this sense, it is seen as a part of artificial intelligence, that you can think of AI as being, machines thinking on their own. Well, to be able to think of their own, they had to be programmed in the first place. So somebody had to code something, but then the algorithm was able to run on its own and improve on its own, so that an artificial intelligence can improve automatically without anybody having to change its source code every time. Machine learning algorithms build a model based on sample data known as training data. I will get into the training data jargon next week, actually. Next week or in 2 weeks. It might be, next week we don't have a lecture, but yeah, it's going to be in 2 or 3 weeks. In order to make predictions or decisions without being explicitly programmed to do so. Another definition given in 1997 by Tom Mitchell is the following. A computer program is said to learn from experience E with respect to some class of tasks T and performance P if its performance at tasks in T as measured by P improves with experience E. So, think of it as one experience is running the algorithm through one sample of data. Okay? Then, the class of tasks could be doing an OLS estimation, estimate the mean, estimate the proportion, find the confidence interval, do any sorts of prediction. Performance measure P is a way to measure how good the algorithm is doing. Of course, we will define what kind of performance measures can be used to assess whether an algorithm is doing good or bad. I mentioned the R-squared for linear regressions. I mentioned goodness of fit. That's a measure of the quality of the estimation. It's one measure among many others. So, machine learning is this idea, or is this process of a computer program improving its performance, so improving its measure P in a specific task as experience increases, as E increases, as we repeat this thing over and over again. Self-driving cars. You probably heard of this by now. They use AI system. The automatic vision system that identifies an imminent accident is machine learning, based on many trips from the past, based on computations between the distance between your car and the car behind you, the car in front of you, the car on the side, based on the speed and so on. The program is going to estimate the safest distance from the next car, and is going to estimate where it's when it's on the road or off the track, and so on and so forth. The more the car drives, the more data it gathers. And the more data it gathers, the better it is going to improve if the algorithm is a machine learning algorithm. Little piece of trivia. One of the first good self-driving cars dates back to something around 1987 or 1988. So that was before I was born. I think it was before all of you were born. I was born in 91. So back then, machine learning was already a thing. And they already had some experiments on self-driving cars that they made browse in some deserted road or in some parking lots. Of course, since there have been many improvements, and the first projects of self-driving cars date back to the 1920s, in fact. Nowadays, we have states in the United States which have allowed the use of self-driving car in circulation. Not all the states allow it, but in some of them, and you can watch YouTube videos about it, you can see a car getting on a highway where the driver is literally sleeping, or the driver is lying down, so if you look at the window, you don't see anybody in the car. And the car is inserting itself into the highway, which requires a lot of computations. Remember, if you go into the highway, you have to look at your blind spot. Is there any car coming? What is their speed? And then you have to try to insert yourself without disrupting the pace of the other cars. It is highly technical when you think about it. And this is where we're at. Machine learning is also used for face recognition in the street. Countries and cities who have cameras in their streets are machine learning algorithm based. So the more data they process, the more faces they capture in the street, the better they get at recognizing some specific traits. In fact, you can find a website online, which I'll try to find for next time or something, where you can play with the machine learning algorithm live, which is about facial recognition. So you have several pictures that you can submit to the algorithm, and the algorithm is going to tell you if it's a human or a dog, or a human or an animal. So you can feed a bunch of pictures, and at the beginning the algorithm is pretty bad. It's like, yeah, that's an animal, whereas it's a human, and so on and so forth. This is due to the fact that each image is composed of pixels. Each pixel is a combination of numbers that represents the color inside that pixel. After feeding sufficiently many pictures to the algorithm and telling the algorithm every time, here you're right, here you're wrong, here you're right, here you're wrong, the algorithm gets better and better at recognizing human patterns as opposed to animal patterns. And the more you click, the more you submit to the algorithm, the better it gets. And eventually the algorithm gets around 99 point something percent accuracy. But I also want to say that machine learning is something you already know about. It is not an obscure black box computer program that just looks like a machine working on its own. The econometrics we did in ECON 333 and so on, OLS regressions, are also a part of machine learning, because some of these algorithms are such that you can feed new data all the time, and some OLS estimators get better and better. You don't need to code this every time. You code it once, and then you just have to feed data to the software, and the software will do the analysis every time. So econometrics as we know it is also machine learning. But the way machine learning is said today, the term machine learning refers to something more AI, more computer-based, but we are already in it, okay? This is one of the reasons I'm going to go over the linear model today again. It is a good benchmark, it should be a good refresher, and it is technically part of machine learning. When it comes to machine learning, we broadly distinguish two types. Sometimes you can see a third type called reinforced learning, but it's outside of the scope of this course. The first one is called supervised learning. When you do supervised learning, you already have a response variable y, an outcome variable y in mind, and you have some associated predictors x, whatever they are. The objective is to estimate or predict a relationship between y and the x's. For instance, regression methods, so linear models and so on, every time you see y equals something with x, you are looking at supervised learning. The other type of learning is unsupervised. It is a case where there is no variable y, only variables x's. So in this case, the objective is not to see or not to predict a variable by other variables, but rather to understand the relationship between the x variables themselves. An example of that is called cluster analysis, that seeks to group observations in categories according to the value of the variables. you have lived an example of that. I assume that almost all of you guys have Amazon. You might even have Amazon Prime because with the student you can get a free 1-year trial or something like that. Every time you go to Amazon and you're about to purchase something, or maybe not, sometimes if you go down on the screen, there is a other customers also purchased, and then it shows you what they also purchased. Or something as all other customers also looked at. This is cluster analysis. Based on the characteristics of each consumer, based on what they clicked on before, based on their search, based on the keywords, and so on, based on the time spent on a given page, they group observations, they group consumers into groups that seem similar enough so that they are likely to purchase those goods as well. So when you get other customers also looked at blah blah blah, there is a cluster analysis, more or less, it's roughly speaking, running in the back that groups you with all of these other customers. Amazon's algorithm judged that you are a similar consumer to all these other consumers who also looked at those items, so that Amazon judged or estimated or guessed that you would also be interested in these items. In general, especially in this course, we will do supervised learning mostly, because in economics, at the end of the day, we don't really care about just grouping observations together. Rather, we are interested in establishing causation facts. We want to know what causes what, and what that variable is, how it causes a given y, a given response variable. We use economic models to understand, try to break down a given economic phenomenon, which is too hard to understand otherwise. And sometimes we take the model to the data, see if the data confirms that indeed there seems to be a statistical causal relationship between those two variables. We care about causation in general, not just correlation, which is why we will be focusing on supervised learning mostly. I will briefly talk about unsupervised learning later in the semester. Okay. Now, let's get into some statistical notation. A random variable, which is usually denoted in uppercase in the course or in many books, it's a variable whose value depends on outcomes of a random phenomenon. For instance, if you flip a coin, whether it's heads or tails is not certain. Sometimes you could find heads, sometimes you could find tails. The phenomenon here is random. You toss a coin. Tossing a coin is a random phenomenon. A random variable then has a probability distribution. It can take some values, it can take some outcomes with a certain probability. So if I think about flipping a coin, and I say, maybe not flipping a coin, throwing one die, a 6-faced die, there is a probability of finding a 1, there is a probability of finding a 2, a 3, a 4, a 5, and a 6, but there is no probability of getting a 7 or a -1, simply because those faces do not exist on a 6-faced die. So we call this a probability distribution because it distributes probabilities, it associates probabilities to outcomes. If I throw a die and the die is fair, then the probability of getting a 1 is 1/6, the probability of getting a 2 is 1/6, and so on and so forth. If x is a random variable, then the probability of x taking a given value small x, small x is a realization, big X is the random variable in general. In this case, we denote it P of x equals small x. P here has a double bar at the front. This is just standard notation. You can use a regular big P. That's understandable. So for instance, if x is something like the number on a die, then the probability that the number on the die is equal to small x, like 1, this probability is equal to 1 over 6. Now, often, when we look at random variables, we look at expectations. Expectation, which we denote E of x, which is an E with a double bar at the front, double vertical bar, is the average value that x can take. So it's a weighted average, and the average is weighted according to the different probabilities. Again, if you want to go back to a 6-faced die, with probability 1 over 6, you're going to get 1. With probability 1 over 6, you're going to get 2, and so on. If you want to take the average, you need to do 1 times 1 over 6, plus 2 times 1 over 6, plus 3 times 1 over 6, and so on, until you get to plus 6 times 1 over 6. When there's an expectation, there usually is a variance. The expectation is an average value. The variance is, on average, how far are we from the average? So it is the expectation of the squared deviation from the mean. Why do we square it? The square is used to show a distance. Whether x is lower than the expectation of x or higher doesn't matter. What matters is that it is far away from it. So by taking the square, we get rid of the minus, and we can look at, on average, how far x is from its expectation. So it is the expectation. This is where we start. So I start with E of the squared. Squared now is here, is the second thing. Then inside the brackets, you look at deviation from the mean, which is x minus expectation of x. It is what we call a dispersion parameter. It tells us how spread out the variable x is compared to its mean. Another distinction I need to make. Often I will talk about population quantities and sample quantities, or population value and sample value. The probability that x is equal to small x, expectation and variance are what we call population values. They are not random. X is random, but its average, it's not random. It's the probability that x is equal to 2 is not random. It's always equal to 50% or whatever number. So note that every time you see the overall notation with double bar, you're looking at real distribution values. Population values can also be called population distribution values. I also wanted to say this, that's just a piece of trivia for you, but some random variables do not have an expectation nor a variance. So, when I say do not have an expectation, I mean that it's not that the expectation is 0, it's that the expectation does not exist. It's kind of strange, right? You're thinking, well, in real life, I observe this value, and this value, minimum and maximum, so the average should be something in between. It turns out that mathematically speaking, it is possible to have a random variable that doesn't have an expectation or a variance. I can think of one in particular, the Cauchy distribution. Cauchy is a very famous French mathematician from a long time ago, and he showed an eccentric case where a random variable doesn't have an expectation nor a variance. It's kind of weird, but it has a probability distribution. In the chat, somebody asks if the variance of x is equal to the expectation of x squared minus the square of the expectation of x. Absolutely, it is the same formula. In fact, one can show that from here, if I expand this computation, I can get to the formula mentioned in the chat. Those two formulas can be used anyway. Sometimes one is easier than the other, depending on what you're trying to achieve. So there is absolutely no problem with that. Good point. As opposed to population values, any statistic derived from a sample is going to be random. Why is it random? Because if you give me another sample, it will be different. Imagine I want to look at the average age of SFU students. If I want to get a population value, I would need, on one given year, I would need to get the age of everybody enrolled at SFU. And then I take the average. That would be my expectation. But if I only have access to a sample, a subset of the students, then I'm going to have a sample and I can find the average age. But this is not the average age of students at SFU in general. It is the average age of my sample. If you take 10 people out of my sample and you bring in 10 new people, the average is going to change. In fact, if you change one student, if you switch one student with another, and they have a different age, my average age will be different again. So, a sample statistic is random. Since sample values like the sample mean, the average age, are random, then if they are random, it means they can also have an expectation and a variance. The variance will then be different from 0. Remember that if a variable has a variance of 0, then it is not a random variable. To understand this, let's go back to the formula of the variance. For this to be 0, it means that x has to be equal to expectation of x every time. Correct? Because all of these numbers are positive. So if I take the average of positive numbers, for this average to be equal to 0, it must be that each distance individually must be 0. Then it means that x is equal to its average. Then it means that x is equal to the same number. Everybody has the same age. So the average age is everybody's age, and there is no variance because there is no dispersion. Because a sample statistic will change across samples, then it will have a variance different from 0, and it will have an expectation. Now, let's get into the entry. Let's talk about conditional probabilities and expectation. So the term conditional here is going to be very important. A conditional probability or expectation fixes the value of the random variable and computes the probability of another random variable given that the first one is fixed. So conditional probability should be interpreted as a probability with a condition. And the condition is that another random variable could be fixed, for instance. Here is an example. The probability that x1 is equal to small x1, given it's a vertical bar, given or conditional on x2 being equal to the value small x2, this refers to the probability of the random variable x1 taking the value small x1, given that the random variable big X2 is already equal to small x2. Adding this condition will give you a different probability for x1 taking the value small x1. The same way I can use the expectation. Instead of a p here, I can put an e, and expectation of x1 given x2 is equal to x2 is the average value of x1 when x2 is fixed at small x2. Let me give you an example to get the idea in mind. Imagine that the world is being composed of circles and non-circles. And we also have smokers and non-smokers. Now, we know that 20% of people are circles and 80% of people are not circles. Then what we know is that among the circles, if I only look at circles, 30% of them are smokers, so 70% of them will be non-smokers. And among the non-smokers, 60% of them are smokers, 40% are not. So here we have two variables. We have, are you a circle or not? And the other one is, are you a smoker or not? So let x1 be the circle status and x2 be the smoking status. So given the data I just gave you, what we know is that the probability of finding a smoker among circles when x1 is equal to a circle is 0.3, because 30% of the circles are smokers. So when I look at the circles in particular, I find 30% of smokers. And equivalently, when I look at circles, if I know they are 30% of smokers, I know they are 70% of non-smokers. Equivalently, I also know that there are 20% of circles in general in the total population. So I also know that the probability of finding a smoker among non-circles is 60%, which is the one I gave here. So if among non-circles I have 60% of smokers, among non-circles I have 40% of non-smokers. Finally, I know that there are 20% of people which are circles, so I have an unconditional probability here, which is the probability that x1 is equal to circle is 20%, and the probability that x1 is a non-circle is 80%. So in words, we know the probability of meeting a circle or non-circle, and we know the probability of meeting a smoker among or given that we are looking at circles or that we are looking at non-circles. This whole thing is very wordy, so I really suggest you to look at it again and again at home until you are confident in what each of these numbers mean. Now, it's important to know what we know, but it is also important to know what we do not know. Given the statistics I just gave you in the previous slide, what we don't know is the probability of finding a smoker. We only know that we have smokers among circles and smoker among non-circles, but overall, we do not know the proportion of smokers in the population. So we do not know the probability of meeting a smoker or meeting a non-smoker. We only know these probabilities when looking at circles or when looking at non-circles. We can find these probabilities using some math, but it's just not explicitly given in the exercise I showed in the previous slide. And among smokers, we don't know how many are circles. Same, among non-smokers, we do not know how many are non-circles. Does it make sense? So in words, we do not know the probability of meeting a smoker, and we do not know the probability of meeting a circle among smokers or among non-smokers. In general, when we learn, myself included, when we learn about conditional probabilities, we very often get things mixed up, and we put numbers on things we do not know, and sometimes we do not put numbers on things we actually know. So make sure you read that again and again, so that all of these terms are clear in your head. Let me give you another example, which I prefer. Imagine that the variable y is the temperature in Celsius degrees, okay? So x, imagine that x is a random variable. It could be either Vancouver or Hasparren. Hasparren is my hometown. It is a beautiful town in the Basque Country. You can check it out online. Beautiful. The average annual temperatures, I found that online, are when x is equal to Hasparren. So when I am looking at Hasparren, the average temperature is 13.5 degrees Celsius. And when I am looking at Vancouver, the average temperature, annual temperature, is 11 degrees Celsius. So you can see here that fixing the condition that I am looking at my hometown in particular or Vancouver in particular, the average temperature will change, right? Because I am simply not looking at the same thing. Now, imagine that Hasparren and Vancouver were the only two locations in the world. If you want to compute the average temperature in the world, then you can take the average of both of these numbers. You take the average of 11 and 13.5, which would be something like, it's 2.5, what is it, 125, 1225? 12 degrees Celsius and 12.25 degrees Celsius is the average temperature in the world here. But when I fix the location, of course, the temperature is going to be different. What I also showed you here, incidentally, is what we call the law of iterated expectation. If I want to find the expectation of y, just the average temperature, I can take the average of conditional expectations over all the possible x's. So if I had a third x, I would take the average of 3 different values to find expectation of y. So I have an expectation for each location, and then I retake the expectation, so that's why it's called iterated expectation, to obtain the unconditional expectation. Is everything okay so far? Let me know in the chat. There's a lot to digest here, but those are terms we are going to need for the rest of the course. So I wanted to define them as soon as possible. Now, what is a statistical model? We in this degree, we often go through economic models where we make a set of assumptions. We look at some outcomes like equilibrium, best response if you're into game theory, and so on and so forth. In statistics, a model is also a set of assumptions, but the assumptions are about the distribution of some data or about their relationships. The equation I showed in the very first slide the population regression equation, is part of a statistical model. It is one assumption that one can make in a statistical model. An easier example, think about an equally weighted six-sided die. The underlying assumption is that, it's a pair, six-sided dice. The underlying assumption is that the probability of one die falling on any number is equal to 1/6. Why is it the underlying assumption? Because I called it an equally weighted. If there is a trick played on the die so that the die falls on 6 more often than it falls on 1, then I would need to know how the weight is allocated to know exactly what the probability of finding a 6 is versus a 1. But this here is a statistical model. I gave you a variable and I gave you the underlying distribution of this variable. That is something to start with. Second example, consider a pair of weighted six-sided dice. Note that here I do not say equally weighted anymore. It is weighted. The underlying assumption is that the probability of a die falling on any number differs depending on what face we are thinking of. If it's a 1, it might be a higher or lower probability than if we are looking for a 2 or a 3. Note that the probabilities could be given to us or not. However, we know the type of distribution that is going to be happening here. It's a discrete distribution where each number from 1 to 6 has a positive probability of showing up. So our job could be to figure out the weighting of the dice. Maybe we actually don't know if it's equally weighted or not, and maybe we have to check based on a sample of data. For instance, I give you a pair of dice. You can throw 100 of them. You can throw them 100 times, the same ones, and see if the probabilities you obtain, how many times you got 6, how many times you got 1, and so on. If this coincides with an equally weighted six-sided die, or with some sort of a weighted six-sided die. These assumptions will have consequences on the properties of the statistical procedures used. So whether I say it's an equally weighted six-sided die or not will have a consequence on the first of all on the tools I'm going to use, and second on how good the tools I'm going to use are. So it is very important to understand why every assumption is made at all times. Assumptions will always be used. The point of a model, remember, in general, but in economics in particular, is to simplify reality. So, in a model, we never include anything which is useless. We never include useless information. The less information, the better, but any piece of information has huge consequences on the rest of the model. So one needs to understand what role each assumption is going to play. Imagine that we wrongly believe that the dice are equally weighted. We think it's a regular pair of dice, but actually it's not. If we think it's a regular pair of dice, we are going to expect a probability of 1/6 for each number. And we are going to play, let's say, gamble at the casino, thinking about those probabilities. But if in reality the dice are weighted, not equally weighted, then our predictions that I'm going to get a 1 with a probability of 1/6 is totally wrong. This is the wrong prediction, and my conclusions will be wrong as well. And that will just this piece of information is going to tell whether I'm using tools that provide accurate predictions versus tools that provide very highly inaccurate predictions. Since we are talking about model, I distinguish, not I, but 3 types of models in general are distinguished. Parametric models are models with a finite number of parameters. In your head, you could think of beta 0, beta 1, beta 2 when you're looking at linear regression. But what's important is the parametric models specify the distributions. In particular, it specifies the distribution of the error term. It tells us it's a normal distribution, it's a uniform distribution, it's a Poisson distribution, it's a binomial distribution, and so on. If you want to estimate a parametric model, in general, you're going to use what we call maximum likelihood estimator. This is not something I want to talk about in this course. I just threw the term out there. Some of you guys might know what it means. For the other ones, it's just a type of method to estimate a parameter, knowing the distribution we are looking at. Semi-parametric model have a bit of both. They are models with a finite dimensional component. Again, think about beta 1, beta 2, beta 3 in a linear regression model. But there is an infinite dimensional component. And what I mean by infinite dimensional component is pretty much there is something that we don't necessarily specify. So, some assumptions are made about the distribution of some random variables, but the distribution is not fully specified. Typically, in linear models, we have a set of parameters, beta 0, beta 1, and so on, but we do not assume anything about the distribution of epsilon, the error term. Sometimes we just say the error term on average is equal to 0. But many distributions have an average of 0. The fact that we don't specify the full distribution makes us deal with a semi-parametric model versus a fully parametric model. Finally, if there is parametric and semi-parametric, there must be non-parametric models. Those are models with an infinite number of parameters and minimal amount of assumptions. For instance, a linear model cannot be non-parametric because we are assuming linearity. In general, non-parametric models are used to predict, not to estimate parameters. So we remain agnostic about the shape of the function f, the one I talked about in the first slide, because we only care about its predictions. So we don't need necessarily to assume it's a straight line, it's a curve in one way or another. What we just need is what kind of tools will make us make accurate predictions. For which type of model is the expectation of the error term 0? The 3 of them, all of them. However, in the parametric model, we assume more than just the expectation. We assume the full distribution, like a normal distribution, for instance. In the semi-parametric model, we only assume the expectation is 0. And in the non-parametric model, we only assume the expectation is 0. But we do not make any assumption about the functional form. So, parametric model has functional form and full distribution. Semi-parametric model has functional form but not the full distribution. And non-parametric model has not the full distribution and no particular functional form. So, parametric models make more assumptions than semi-parametric models, which in turn make more assumptions than non-parametric models. Assumptions come with an advantage, but they also come at a cost. and I will go over this today and in the next 2 lectures. So the models are, yes, the model on average are correct. That's what it means. When the error term is on average equal to 0, it means that on average, we are correct. Yes. But that's only on average. So since I'm talking about assumptions, let's get into their role in a model. Assumptions have a crucial role on for the properties of the estimators. The more restrictive they are, think about parametric model is the most restrictive, the better the properties of the estimator. But is it always worth making restrictive assumptions? So if you make a lot of assumptions, then it's great. Your tools are going to work wonders. The problem is, the more assumptions you make, the less realistic your model might get. If you're confident that your data is normally distributed, you plotted your data and you found a bell curve. It's like, looks like a bell curve. I think it's a rather normal distribution. Assuming it's normal distribution will make your statistical predictions even more accurate. However, if in reality your data is not normally distributed, but you think it is, then your predictions will be made based on normality, but there is no normality. So your predictions might not be good if your assumptions are not properly backed up. And this is the same the other way around. You might think, well, why do I assume things then? It's true. Assuming as little as possible ensures that we're going to stay realistic to some extent. However, the tools we are going to use will then come with drawbacks because we're not restricting the model. Moreover, some assumptions are purely technical. So it's pure math and stats where you need this to go from one equation to another. And they're just needed for estimators to have desired properties. It can be hard to verify sometimes. Some conditions are very hard to verify, and some conditions look very restrictive, and at the same time they're hard to verify. Other assumptions are based on common sense. They are based on your knowledge of the data. They are based on intuition. They are based on maybe some kind of model. Economic models, in general, make some assumptions that we can take to reality or not, depending on how realistic they are. Given the data at hand, does it make sense to assume this or that? I mentioned assuming a normal distribution. You can look for a normal distribution in the data, and if you see it, then maybe you can tell your audience, yeah, I think it's normal, look at it, looks pretty normal to me, so I am going to make this assumption to have better properties for my estimator. But sometimes there is evidence in favor of an assumption or not. And sometimes you might want to make an assumption, but you find no evidence for it, or you find evidence against it. In which case, you have to move on to another statistical procedure. And I will get into this once we talk about the OLS estimator. So, depending on the assumptions, one estimator might be preferred to another. So, since I'm talking about estimators, let's define what an estimator is, and let's see what the properties of an estimator, or the desirable properties of an estimator, are. The definition is simple. An estimator is a rule to compute an estimate of a given quantity given some data. Give me some data. What do you want to know? The proportion of smokers, the average age of students, the impact of a tax on gasoline on the consumption of gasoline. The estimator is going to tell you how you should find your estimate or your prediction. We also use the word estimator when we talk about predicting. So it's a rule. The OLS estimator is a formula. The formula is a rule that you apply to your data, and that gives you an estimate of the quantity. So an estimator is no more than a rule to produce a guess, educated or not. If, for instance, we have a chat and you're asking me how young students are in economics, I can provide a bunch of different estimates. The first one could be the estimates out of my butt. I could say, given my experience TAing and teaching, I think that the average age of a student should be 23 years old. Another person could estimate something else based on a student, for instance, could give me his own estimate based on the age of his cohort or based on what his friends told him. Those are other estimators. They are probably less educated, but why not? Maybe my estimate is accurate. Or you could give me some data of the age of SFU students, SFU Econ students every semester for the past 5 years. And every year I could compute the average age or something like that. That would be another estimator. Now, remember, if we had access to the population data, it would be great. I could use it to find expectation of X. If I want to know the average age of SFU students, and you give me all the record of SFU students every year for the past 10 years, great. What I'm going to compute is not a sample average. It is an expectation, because I have all of the data. In reality, of course, it is impossible or very difficult to obtain all of the data. So since we only have access to a sample of it, we are going to use an estimator to compute an estimate. What I want to estimate is expectation of X. But since I don't have all of the data, I cannot know it with certainty. What I can do, however, is use a sample to make a guess about it. Now, since the true number I'm looking for, expectation of X, can be obtained with all of the data, ideally, if my sample is getting bigger and bigger, closer and closer to the full data, then ideally my estimator should get me closer to the truth. Make sense? As I get closer and closer to the full data, then I would like my estimate to get closer and closer to the true number it is trying to estimate. Estimates come from samples. So, like other sample statistics, an estimator is going to be random, and it will have an expectation as well as a variance. So, if you compute the same estimate over a bunch of different samples, should tell us something reliable on average. I say so, but it is not always the case. I'm saying that it would be ideal for an estimator that if I use the same estimator on different samples, not bigger, it could be the same size but different ones, then on average, what I am looking for, what I'm trying to estimate, or my estimate on average, is close to the true thing I am trying to estimate. That would be desirable. So that what I could do is every year get a sample of SFU students and compute the average age. Let's say I do this 10 times, I would get 10 different average ages. Then I can recompute the average of those 10 averages, and hopefully it would take me closer to expectation of X. But again, ideally. Now, since an estimator is random, we would like to use its distribution to infer something about the true value of the parameter of interest. Getting closer and closer is great, but we don't know how much closer we are. However, an estimator has a distribution, and if the distribution contains the true value, E of x, then maybe I can play around with the math to say something about the true number based on my estimates. This is what we call inference or hypothesis testing, which I'm going to get into later in this lecture. Any questions? This slide is very important. All the slides are, but this one is very important to understand what an estimator is and what we ideally would like to get from it. Okay. So, given what I said before, let's mathematically define these desirable properties of estimators. First of all, definition. An estimator x hat, so whatever it is, whenever there's a hat, I'm talking about an estimate. An estimator of a non-random quantity x, so I'm trying to estimate a value x. Here I write big X, but that could be a small x as well. It's just a non-random quantity. An estimator x hat is said to be consistent, or we also say asymptotically unbiased, if it converges in probability towards the value it is trying to estimate. And we write it as x hat, arrow with the p with a double bar, x. Every time you see the word asymptotically or consistent, you have to think about the sample size, n, goes to infinity. Okay? So this means that my estimate, if I keep computing it on a bigger and bigger and bigger sample every time, should get me closer and closer and closer to the value I am trying to estimate. In statistical terms, what it means is that when n increases, as I increase the size of my sample, the probability that x hat is at a distance of at least epsilon from x, far away by a distance of epsilon, goes to 0. It means that if I choose a distance epsilon, when my sample is getting bigger and bigger and bigger, the probability that my estimate is that far from the true value goes to 0. Conversely, I could just make the opposite statement. I could say that the probability of the distance between the two numbers being lower than epsilon tends to 1. As my sample gets bigger and bigger, the probability of x hat being closer and closer and closer to x, this probability goes to 1. That's consistency. This is usually the first property we look for in an estimator. If an estimator is not consistent, in general, we won't even bother using it, even if it has all kinds of other nice properties. If it is not consistent, it means that when my sample is big, my estimate might not be even close to the real thing I'm estimating. So it's kind of unreliable. Note that I'm talking here about the case where the sample size grows bigger and bigger. This is what I call n. Second definition. An estimator x hat of a non-random quantity x0, maybe I could put a 0 here as well, is said to be unbiased if, on average, it equals the true value of the quantity of interest. It is a very important result as well. It means that if I repeat my estimates over multiple samples, and the samples could be the same size, it's important. The samples could be at the same size. If I take the average of all of my estimates, I should be equal to or close to the true value of the parameter we try to estimate. Think about the bias as being something like a rifle. If you go to the PNE or any sort of theme park, you might find those stands, those booths where you can take a rifle. It's you can shoot lead onto balloons, and if you shoot that many balloons, you get a prize. You might not know this, but when you take the rifle in your hands and you align it with your eye, you might think that the rifle is going straight, but often, if you look at it from further, the cannon is slightly crooked. In this case, we would say that the rifle is biased because on average, it is not targeting what it is supposed to target. It is supposed to target it's supposed to have a straight aim, but on average, it will have a crooked aim. That's actually how I learned about unbiasedness back in my second year university. That's pretty much the example my professor used. Is a consistent estimator always unbiased? No. Those two conditions are very separate. In fact, it is possible to have a consistent estimator which is biased. Most of the ones we're going to see in this class are consistent, but they are biased. And vice versa. We can find estimators which are biased, but they are not, which are unbiased, but they are not consistent. So if I compute the same estimates over and over again on different samples, on average, I'm closer and closer to the truth. But if I get a bigger sample, I am not getting closer to the truth. It's weird, eh? But those are, in general, mathematical eccentricities. But I can provide you an example with that, of each case. Consistency is first, in terms of importance. Unbiasedness is second. So if something is consistent but biased, it's fine, we can still use it. Why? Because look, a consistent estimator is also said to be asymptotically unbiased, which means that when n goes to infinity, then the bias gets lower and lower. That's why the estimate converges towards the true value of the parameter it estimates. So, on a fixed sample, let's say you have a sample of 100 observations, your estimate could be biased. But if you go from a sample of 100 to 1000, you get closer to the truth because when the sample increases, the bias decreases. So, on a given sample, you will always be biased. But if your sample is very, 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 very big, the bias will be very, 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 very small. Still biased, but a tiny bias. Does it make sense? Okay. So, as I just said, many or even most estimators are biased. And in fact, I am going to go over one estimator which is unbiased in this whole course. Everything else will be biased. But you will see that this is in general not a problem as long as we have consistency. If you have consistency, just get a big sample. The bias will be tiny. In fact, for some estimators, we can have an idea of where the bias is going. So we can have an idea whether we are overestimating a quantity or underestimating a quantity. So we can have an idea of whether our estimate is too high, probably too high compared to the true value, or probably too low compared to the true value. That's not bad. At least it can tell us an idea of the direction of the bias. But consistent makes them reliable given the sample used is big enough. If an estimator is consistent, the bigger the sample, the more accurate the estimator and the closer the estimate is to the true value. Okay. Now I'm going to get into linear models. So since I've done all of my definitions and now we're going to get into the gist of the course, why don't we take a break? It's been an hour and a half almost already. I'm sure that your brain by now should be half fried. Mine is a quarter fried. It's hard to speak to computer. So let's take a 10 minutes break. It is 3:53 right now. Let's start at 4:05. Okay? See you soon.
That might not be applicable to you or to the general public of judo players that want to succeed. That, by the way, at the shallow level might be true. Might be true. The point is, there might be a body of knowledge that's yet to be discovered and explored that Koga opened up. That I wanted to understand why his technique worked. It made no sense to me that with a single foot, like the way you turn the hip, the single foot that steps in, why does that work? Because it was actually very difficult to make work for me as a white belt in the very beginning. It doesn't make sense. Like people just, they don't get loaded up onto your hip. Anyway, for people who don't watch Koga highlights, watch Travis Stevens highlights, but the details of the technique don't make sense. But when mastered, it feels like there's something fundamental there that hasn't been explored yet. It's like Koga and Travis made me think that we don't know most of the body mechanics involved in dominance in judo. Like, we just kind of found a few pockets that work really well. The Uchimata, there's these different throws, Osotogari. I wonder if there's like totally cool new things that we haven't discovered. And that Seoinage gave a little peek, because there's very few people that I'm aware of that do it the way Travis and Koga did.
May I ask you a question?
Yes.
The choice of standing Seoinage, I should say this for your listeners. They're probably thinking, what the hell are these two guys talking about? Seoinage is one of the more high percentage throws in the Olympic sport of judo. Probably Uchimata is probably number one, and variations of Seoinage would be in the top 5 for sure. The basic choice you have in modern competition is the more difficult standing Seoinage, where you literally are up on your feet and you perform a shoulder throw that takes your opponent over from a full standing position. The most popular form of Seoinage in modern competition by a landslide is not the standing version. It's a drop Seoinage where you go down to your knees. This means you have a much easier time getting underneath your opponent's center of gravity. The defining feature of any Seoinage is getting underneath your opponent's center of gravity and lifting them. The seoi literally means to lift and carry. Why did you choose the more difficult version? What was your motivation? You know, you're a smart kid. You know right from the start that for every standing Seoinage, there's 20 drop Seoinages in modern competition. One is obviously more high percentage. One obviously works for a wider variety of body types. The number of people who are successful with standing Seoinage is dramatically lower. And it appears to be a move which is completely absent in the heavyweight divisions and rarely seen in the lightweight divisions. Why? What was the motivation? Why did you willingly adopt the less high percentage over
This would be very
the more high
interesting.
percentage?
I would love you to break it apart, because I apply the same kind of thinking to basically everything. I mentioned to you offline, there's these Boston Dynamics Spot robots. When I first met Spot, I fell in love. I don't understand what exactly, but there's magic there. And I just got excited by it. And that fire burns. I want to work with these robots. I want to work with robots. I felt like there's something special there that I could build something interesting with, create something interesting with. And the same with the standing Seoinage from Koga and Travis. I just fell in love with that technique. Just even watching, I didn't even know what the hell to do with it. Was
it aesthetic? It's the standing Seoinage is more beautiful in execution. There's no question.
In my own, we're talking about love here, right? In my own definition of aesthetic, yes, it's not just beauty, because you could argue there's more elegant, sort of Uchimata is very beautiful and effortless. I love something about the dominance of it. I love the idea in sport of two people that are the best in the world and one of them dominating the other. And to me, the standing Seoinage, you're lifted off your feet. And especially when it's done perfectly and with really strong resistance from the other person, it results in a big slam. And that was like beautiful to me. That's the Alexander Karelin, like big pickups. I love that.
It's interesting though. You're correct insofar as you're not just going with aesthetic and the sense of beauty, but you are making, as it were, value judgments about the throw. And that's fascinating to me, because there's two elements to any grappling sport. I'm always insistent upon the idea that jiu-jitsu is both an art and a science. Okay, it has scientific elements insofar as it works according to the laws of physics and lever and fulcrum, et cetera, et cetera. But it also has an aesthetic element insofar as you're making choices with technique. You're expressing who you are as a person. You have 10,000 different variations of moves you could use, but you're specifically choosing these. That's an element of choice and self-expression on your part. And insofar as that is true, combat sports are not just a science, but they're also an art. So most combat sports have this sense in which they have the features of both an art and a science. And it's not just about high percentage in your case. I mean, me personally, I'm obsessed with percentages. What are the ways
That's
to make
the science
you win?
part.
Yeah, but that's also choices
Strategy
involved.
and-
Yeah. But there is an undeniably aesthetic element to martial arts where you, as it were, express who you are as a person in terms of the techniques you're ultimately going to choose.
Does that get in the way? Do you allow yourself to enjoy the aesthetic beauty of a technique?
Of course, yeah. When martial arts are done well, it's the most beautiful sport in the world. Okay, when it's done poorly, it's the ugliest. But a beautifully applied submission hold, a perfect throw, a superbly set up takedown are among the most difficult techniques to execute in all of sports. And when they're done well, they're magic to observe.
But do you prefer certain techniques over others because of their, like, for example, I'll tell you, for me, chokes of all sorts, with the gi, without the gi, probably with the gi is the most beautiful to me, personally.
I value them above all others. People mostly associate myself and my students with leg locking. They're usually rather surprised to learn that I actually value strangleholds far above leg locks. But not for aesthetic reasons, for effectiveness. We can talk about that later if you wish.
Well, let's step back.
Sorry, we drifted awfully far off topic there.
I think this is beautiful. We drifted along the river of life and martial arts. Can you explain the fundamentals of jiu-jitsu?
Yes. If I couldn't, I wouldn't be much of a coach. Jiu-jitsu is an art and science which looks to use a combination of tactical and mechanical advantage to focus a very high percentage of my strength against a very low percentage of my opponent's strength at a critical point on their body, such that if I were to exert my strength upon that critical point, they could no longer continue to fight.
Well, that's about weapons and defenses. But then, is there something more to be said about the set of tools that we're talking about?
That's where the art comes in, because ultimately you have a set of choices, and those choices that you make will be an act of self-expression on your part. Some will prefer this, some will prefer that. That's where you come in as an individual.
That's an overall definition of jiu-jitsu, of being a set of choices that where you're using the things you're powerful in versus the things your opponent is weak in.
No, I was only talking about percentages of body strength. If I have, for example, let's say we have two athletes, athlete A and athlete B. Athlete A has 100 units of strength, however we define that overall. Athlete B has 50. Okay, so ostensibly, athlete A is twice as strong as athlete B. But athlete B can maneuver his body into a set of positions focused around a critical point of his opponent's body, where he can apply 40 units of strength out of his total of 50. His opponent can only defend with 20 units of strength out of his total of 100. You have now completely reversed the strength discrepancy. Originally, athlete A was twice as strong as B. Now, on that one localized point, the knee, the elbow, the neck, B is now twice as strong as A. Under those circumstances, B should win.
I guess what I'm trying to get at, by the way, that's really beautifully said, is what you just said could be applied to other games, other battles. It could be applied to the game of chess. It could be applied to war.
Most obviously in war. I think about, for example, the American strategic bombing campaign in World War II. The 8th Army Air Force was tasked with the idea of destroying German industry. Did they attack all of German industry? Of course not. That would be stupid. They attacked the ball bearing industry. Why? Because almost all of modern machines require ball bearings in order to operate. In order for the mechanical interfaces of machines to operate, you have to reduce friction. It's done through ball bearings. If you knocked out one tiny component of German industry, the ball bearing industry, the rest of it couldn't operate. So too with the human body. I don't have to fight your whole body. I just have to fight your left knee. If I can break your left knee, the rest of your body is irrelevant to me.
But then isn't the art of jiu-jitsu discovering the left knee, discovering the weak points?
Yeah, a huge part of jiu-jitsu is understanding the strengths and weaknesses of the human body. There's parts of the human body that are shockingly robust, and there are other parts that are shockingly vulnerable.
Okay. Got myself a tea, ate a bit. I think we are ready to go. Are we not? Okay, is everybody back in? Throw me a yes or something like that on the chat. Okay, let's go. So, after talking about random variables, population data versus sample data, expectations, conditional expectations, variance, estimators, consistency, machine learning, estimation versus prediction, let's get into the most standard tool one ever studies in economics and even in statistics: linear models. So the linear model is since it's a statistical model, it's composed of a bunch of assumptions. The first assumption is called linearity. Assumption 1 writes the function f from before as a linear combination of the x's, and to each x is associated a coefficient. Now let me explain to you the notation here. Yi is the dependent variable, xi is the vector of independent variables or covariates or explanatory variables. Here I consider k of them. It goes from x1 to xk. And if you want, you could include the first component as the intercept. Remember that if you want to have an intercept in a linear regression, one variable could be just a bunch of ones, and that is the vertical intercept. If all of the x's are equal to 0, this is what y would be equal to. Now, I talked about the fact that I am including k random variables here. However, on the formula, it only shows xi. This is because my notation is a compact notation. In fact, what I should write is xi1 times beta1 plus xi2 times beta2 plus xi3 times beta3, and so on and so forth, plus epsilon I. I take all of these variables into a row vector, into a column vector, and the prime here is not a derivative. It represents the transpose of a vector. My vector is vertical. The prime is going to turn the vector into a horizontal vector, a row vector, and when I multiply this vector by a vector of betas, here beta 0 contains beta 1, beta 2, beta 3, beta 4, all the way to beta k. When I multiply a row vector by a column vector, I multiply the first components plus the multiplication of the second components plus the multiplication of the third, and so on. And that gives me xi1 beta 1 plus xi2 beta 2 plus xi3 beta 3, and so on and so forth. So this is just a way to make notation more compact. I will not ask you to know linear algebra in this course, do not worry. But I want to expose you the most up-to-date notation, which is a bit more technical than what you might have seen in former courses. So since there are k different x's, there are going to be k different betas. So beta 0 is a k-dimensional vector of parameters of interest. Finally, epsilon, as said as before, is the error term. Note that this model has a finite set of parameters. We have k parameters, which are embedded in the beta 0 vector. So this model is either parametric or semi-parametric. It all depends on the assumptions I'm going to make about some distribution. And here it will be about the distribution of epsilon I. Note as well that the model is linear, but it's not linear in x. It is linear in beta 0. That's very important to understand. So let me make a quick detour to explain what I mean. Look at this regression model. yi equals beta 0 plus beta 1 xi1 plus beta 2 xi1 squared plus epsilon I. This model is also a linear model. What matters is that the coefficients appear linearly. Even if I take a transformation of x which is not linear, I take the square, I take the log, I divide by another variable. As long as the betas show up linearly, then we call this a linear model. For instance, if I write xi prime beta 0 squared plus epsilon I, then I don't have a linear model anymore. Because if I want to expand this thing remember inside is xi1 beta 1 plus xi2 beta 2 plus xi3 beta 3 plus xi4 beta 4 and so on. If I take the square of that, I need to take the square of each term plus the double product. This means that at some moment I'm going to have some beta 1 squared that will show up, or some beta 2 squared, or some beta 1 times beta 2. Then we will say that the model is not linear. So the first assumption says the model is linear in the parameters. The parameters are the betas. I also want to emphasize that when I write models in a general form, I use uppercase letters, because here this is the general form linking those two random variables. Once I take that to a sample, I can replace big Y by a small y and big X by a small x to say that I observe realization of Y. Big Y could be the height of somebody in general. It's random. My height is not the same as yours, and so on. When I take this to the data, I would say, oh, I observe the height of Mr. I. It is 5 feet 8, 5 foot 8 or something. So this will become a small y. The second assumption is also pretty important. Well, they all are, but I'll explain why they are important. The second assumption is that an independent and identically distributed, or an IID, sample of the data is available. This means that all the x's, xi and xj, so the x of two different persons, are not correlated. They are independent and they are identically distributed. They come from the same distribution. They are a pick from the same distribution. Same with y. So of course, x and y, xi and yi could be correlated, because in our model anyway, we explain y by x. But here we are assuming that yi is not correlated with xj. So my height is not correlated with your weight. Your weight and your height are correlated. My weight and my height are correlated, but my weight and your height are not correlated. My sample has size n. It is the standard notation in general. So I refers to one person, one observation, and we go from 1 to n. There are n observations in total. Note that for assumption 2, I now use lowercase letters because the sample is what I actually observe. I actually observe realizations of big X and big Y. So now I use small x and small y. Assumption 3 is something I talked about, but here is the technical definition. The error term epsilon has an expectation of 0 conditional on xi, so I need to use a conditional expectation. Expectation of epsilon given xi is equal to 0 for any I. So for me, as well as for you, as well as for someone else, on average, if you fix everybody's x, everybody's error term on average is equal to 0. In words, if you fix xi to any value small x, whatever the small value is, the error term epsilon I is on average equal to 0. So if I look at individuals for which x is equal to small x, then their error term is equal to 0 on average. Note that if this is the case for any x, then whether x is equal to 1, 2, 3, 4, or 5, every time the average of epsilon is 0. So it means that the unconditional average of epsilon, so expectation of epsilon without any condition at the end, will also be 0. And that brings us back to the remark made at the beginning of the lecture. This assumption is going to be also particularly important, especially for the OLS estimator. Thanks to this condition, if I look at the conditional expectation of y given x, so if x is fixed at a small value, at a value small xi, then the average of y will be equal to the average of xi prime beta 0 plus epsilon I. This is just replacing by the expression from assumption 1. This is yi by assumption. Now, if xi is equal to small xi, then I have to replace this x here, this big X, by a small x, because I am fixing big X to small x. And since the expectation of epsilon I here given xi is equal to 0 by assumption 3, the second term disappears, and what I am left with is that on average, if big X is equal to small xi, on average, y is equal to xi prime times beta 0. Does it make sense? So again, this is saying that on average, we are not making any mistake. Neat. This is the consequence of assumption 1, 2, and 3. You might not realize, but in this computation, I also use, do I use? No, actually I don't even use assumption 2. Assumption 2 will be used later. And so again, the conditional expectation of yi given xi is linear in beta 0. Assumption 4. Assumption 4 is more technical, but there is also an intuition behind its statement. So, if I take all of my x's, for each person, I observe k different variables, correct? I observe age, height, weight, number of kids, income, and so on. If I put this in one row, and I take everybody's data and I stack them in rows, then I'm going to have n different rows because I have n different observations. And since for each observation I observe k different things, then I'm going to have k column. If you put all of that into a table or a matrix, then we get n rows and k columns for the matrix X. I call it X for notation. Big X can also mean matrix notation. So the n times k matrix X gathering the observations xi has rank k. What I mean by rank is a technical condition coming from linear algebra. You don't need to know exactly what it means. You just need to know what it is by heart. It is full column rank. This assumption is also called no collinearity. You're right. It's not that it's no null space, it's that the null space is equal to 0. The only vector that can make those things equal to 0 is the vector of zeros. That's a technical mathematics statement, so don't worry guys, that's not a big deal. What you need to understand is no collinearity. And I will explain this in a minute. Lastly, assumption 5 is what we call homoscedasticity. Try to say that fast multiple times in a row, good luck. But it's a good one to say in a family dinner around Christmas if you want to show off about what you learn at university. Because chances are nobody knows this word exists, but economists. Since epsilon is random, it has an expectation, and in assumption 3, we assume the expectation was 0. In this assumption, we assume that the variance does not change with observation I. So the conditional variance of the error term does not change with I. It is always equal to sigma squared. So this assumption states that the variance of the error term doesn't depend on what x is actually equal to. You see here, I say conditional on x, and by conditional on x, I'm saying that I am fixing big X to a small x value, which is why now it becomes a small x subscript y, subscript I here. So whether you're looking at somebody who's 10 years old, 20 years old, or 60 years old, the variance of their error term is the same every time. Those are the 5 fundamental assumptions of the linear model. Sometimes some assumptions cannot be made because of the data at hand or because of the model that we are using to back up these assumptions, and so on. But with those 5 assumptions, we can use the OLS estimator and obtain reliable predictions. So let's go back to each assumption in detail and see what they imply. So assumption 1, you can click on 1 here, gets you to the assumption, assumes the form of the relationship between y and x. A linear form makes the coefficients easily interpretable. Think about a coefficient beta associated to a variable xi. It represents the marginal effect of xi on yi. Remember, in economics, every time we talk about marginal, we are talking about a derivative. If you go back to assumption 1, boop, you can see that if I take the derivative of y with respect to any of the x's, since it's a x1 beta 1 plus x2 beta 2 and so on, if I take a derivative with respect to x1, all the other x's are going to disappear, and the derivative is going to be equal to the coefficient in front of x1, which in this example would be beta 1. So if beta is the coefficient associated to xi, when I take the derivative of y with respect to x, I get beta, keeping all the other x's constant, as usual. So this means that if somebody has a certain vector of x's, he has a certain height, certain weight, certain income, certain number of kids, he lives in a certain place, certain marital status, smoking status, and so on. If I increase his age by 1 year, the effect on y will be equal to the beta that is associated to the age variable, keeping everything else constant. So I am looking at somebody who's the same as before, but you increase his age by 1 year. Everything else is the same. He is still a smoker, same height, same weight, and so on. How is this going to affect y? This question will be answered with beta. So it's an easy interpretation of what we call the marginal effect. In economics, we are very often interested in marginal effects because we want to see how increasing, let's say, a price by $1 or 1%, how this will affect the demand for a certain good. So we don't want to necessarily predict the consumption of a good next year or something like that. We just want to see if this tiny thing changes, just that thing, how this alone will impact the outcome variable. That's, for instance, what we do if we are trying to estimate elasticities. Assumption 2, the IID sample, is needed to show the consistency and asymptotic normality of the OLS estimator. So, what I want to say here is that it is needed for technical reasons, but if we don't have that assumption, we can use other technical tools, other statistical theorems, to also get consistency and asymptotic normality. I will get to asymptotic normality soon, don't worry. So it's a technical assumption which is very useful and also most of the time easy to make if you know how the data was gathered. If you make a survey of students, chances are that students will not be correlated with each other in their outcome if it's a random survey. So any kind of data coming from a survey will be IID. So in general, assumption 2 can be made because we know that the data has been gathered in such a way that the random variables are IID. Assumption 3, if you remember, is called exogeneity. It is the fact that the conditional expectation of the error term is equal to 0. It is also needed to show the consistency and asymptotic normality of the OLS estimator. This one is needed. Without it, we cannot show consistency or asymptotic normality. And in fact, next week, or in 2 weeks, I will go over conditions where assumption 3 cannot be made, is not valid, and in this case, we cannot use the OLS estimator anymore. So I will go over some solutions, remedies, alternatives. Assumption 4 is about collinearity. It is needed to show the consistency and asymptotic normality of the OLS estimator again. It is what we call a regularity condition that is going to rule out collinearity. Collinearity, I made a statement about the null space and about the full column rank. Collinearity in words means that some x's are not linearly related to each other. So if, for instance, in my data, I have a temperature in Fahrenheit degrees for one x, and the same temperature in Celsius degrees in another x, then I have collinearity, because if you want to go from Fahrenheit to Celsius degrees, you just need to apply a linear conversion. I believe it's 1 degree Celsius is 32 degree Fahrenheit, or 32.5, plus 1.8 times the number of Celsius degrees. This is also rather easy to verify in practice because you can look at your x's and you can look for which ones are highly linearly correlated. Assumption 5 is optional in the sense that the OLS estimator will still be consistent and asymptotically normal. No problem with that. But if we make this assumption, we're going to have one more nice property, which is called BLUE, Best Linear and Biased Estimator. So, what do we do with this linear model? What are we trying to achieve? Why make all of these assumptions? And some of them are hard to verify. Well, we do not know beta 0. We want to learn about it. We would like to know it. We don't have access to all of the data in the world. We only have access to a sample. So, we are going to estimate beta 0 using what we observe, yi and xi in lowercase. Note that, again, the OLS estimator is only one but many different rules to make an estimate of beta 0. I could come up with an estimate as well. It could be a ballpark estimate. It might not be very accurate. Probably not. But we want to be more educated in the estimate we're going to make. And given the nature of the relationship, assumption 1, by estimating beta 0, we will also be able to make predictions. But since we make a very strong assumption, which is that the relationship between beta 0 and y is linear, the goal here is clearly to estimate before predict. If we were interested in predicting only, we would not assume a linear relationship. Rather, we would say, I don't know what the shape looks like. I don't care about the shape. I just care about making good predictions. Here, we make an assumption about the shape because we care about the nature of the marginal effect. So, finally, let's get into the OLS estimator. So, the OLS estimator looks for the straight line that approximates the data the best. We have a scatter plot of data. We want to run a straight line through the data, but this straight line has to be close to the data in some sense. So the estimate beta hat, in order for its line to be well located, beta hat is going to minimize the average distance between what we observe and the approximation we're making out of it. So I observe yi, and I want to use my x's to make a prediction, a linear prediction. So I want to minimize the distance between the points on the scatter plot and the corresponding prediction on my straight line. I take the square because whether the distance is positive or negative, whether the observation is above or under the straight line, doesn't matter. All that matters is that the straight line is close enough to all of these points on average. So here I can take the sum of all of these distances. In fact, I can put 1 over n in front to make it an average. I did not put it there because it does not matter mathematically. But to be more exact, I would like to minimize least squares. So the argmin means least. It means the argument of the minimum. So beta hat, is going to be what minimizes this. And this is the average distance between the data and our approximation or our future prediction. Since you're trying to minimize a function, I think that by now you know your calculus. We can take the first order conditions, take the derivative with respect to each beta, because remember, here we have k different betas. So we have a bunch of them. We have k first order conditions. And if you take the derivative, make it equal to 0, and so on and so forth, and rearrange terms, you end up with the OLS estimate beta hat OLS, which after reorganizing all of the observations in vectors is equal to x prime x, so the transpose of this matrix times itself. Then I take the inverse of it, so the inverse of a matrix is kind of a generalization of the inverse of a number, but there is a whole formula to compute it. Don't worry, you don't need to know it. I just want to show you what the formula looks like. Then you multiply this by the transpose of your matrix, and finally times your vector y, which gathers all of your yi's. So it's going to be a column vector, one column, and each row is the observation y for each observation. So we get n different rows in that vector. N by 1 here stands for n rows, 1 column. And n by k stands for n rows, k columns. So this is what happens if you have a bunch of different x's on the right hand side. It gives you this formula. You might be more familiar with the formula with one single covariate and maybe an intercept. So let's look at the univariate regression. It is no more than a special case of what I just showed you. So the model now is yi equals an intercept beta 0 plus beta 1 times a variable x plus, as usual, the error term. If you do the same computation as before, take the first order conditions and blah blah blah, you actually get to the following result. Beta 1 hat, so the coefficient associated to x, is estimated with the ratio of the covariance between y and x, how they covary together, divided by the variance of y. Beta 0 hat, the estimate of the intercept, is equal to the average outcome variable, y bar represents the average, minus the previous coefficients we found, this thing, beta 1 hat, times the average x. This is saying that, this second result is saying that your regression line is going to go through the middle point of your data, the point x bar, y bar. Any questions? You will need to know this one for the exam, but I would not ask you to know the one with the matrix notation. I just wanted to show you the full formula. So this is no more than one guess among many other guesses. It is more or less educated. I would say it's more educated than my personal ballpark guess because of the properties of the estimator. And here is the first one. If assumptions 1, 2, 3, and 4, so I mentioned that those 4 were needed, then the estimate I just obtained gets closer and closer to the real vector, the real parameter I am trying to estimate, as I increase the sample size. So every time I run my regression on a bigger sample size, the result gets me closer and closer to the truth. I use the same notation as at the beginning of the lecture. The probability that beta hat OLS and beta 0 are far away by at least a distance epsilon goes to 0. Why? Because they're getting closer and closer. So the probability that beta hat OLS is closer to beta 0 than a distance equal to epsilon tends to 1 because it gets closer and closer. Closer and closer as I increase the sample size. And here I wrote the same statement in words for you to get used to. This is the most fundamental result. Because it's consistent, it pretty much says that if you get a sample which is big enough, you can trust the number you are going to obtain. You cannot trust it in the sense of it is the reality. It is not. It's only an estimate. But if the sample is big, it is close to the true number. Based on that, you can then make predictions and make conclusions and say, I think that, let's say if you're in a firm, you could say if you increase advertising on YouTube by $1 million, then it will increase your profits by this amount. That's the kind of conclusion that you can take with the OLS estimator if assumptions 1, 2, 3, and 4 are satisfied. But that's not all. The second result is even nicer. If assumptions 1, 2, 3, 4, and also 5, the one I called homoscedasticity, are satisfied, then square root of the sample size times beta hat minus beta 0 converges in distribution. So instead of a P now I have a D, to a normal distribution, which on average is equal to 0, and its variance, so the variance of this thing, is equal to sigma squared times the inverse of this matrix. Again, I won't ask you to know this by heart, but I still ask you to understand how it works. Imagine that square root of n is out of the picture. Remove it. Then, beta hat OLS minus beta 0, why would it converge to a random variable? We saw in the previous theorem that it converges to the actual number. So, one minus the other should converge to 0. Just to 0, not a random variable. Now, since in the brackets we are going to 0, n goes to infinity because it converges in distribution. It's asymptotic. So on one hand, we have something that tends to infinity. On the other hand, we have something that tends to 0. And if you remember your formulas in mathematics, something that goes to infinity times something that goes to 0, in general, is uncertain. We do not know if the end result is going to be 0 or if the end result is going to be infinity. It depends whether the infinity term goes to infinity faster than the other term goes to 0. This theorem is saying that this goes to infinity, this is multiplied by something that goes to 0, and yet when you multiply them together, it tends towards a normal distribution. So it will go towards a random variable that on average is equal to 0, but can take a bunch of other values. And those values will be aligned on a bell curve. This theorem is an application of the central limit theorem, which says that as the sample size increases, square root of n, it's always square root of n at the front, times the estimator minus the value it estimates, tends to a normal distribution with mean 0 and the finite variance. Note that since here we make n go to infinity, on average our normal distribution is equal to 0. Why? Well, because of consistency. We know that asymptotically the estimator is unbiased. Asymptotically unbiased is the same as consistent. So, asymptotically, when n is equal to infinity, this thing is on average equal to 0. The part in the variance, the inverse of this is a matrix, you don't need to know it by heart, is the inverse of a matrix, but you can see here that we have some x and some x prime. So, this is some sort of a covariance matrix. It is a covariance matrix. If two variables are linearly correlated with each other, like the example of Fahrenheit degrees and Celsius degrees, then this object, this quantity, will not work because of the -1. Remember that 1 over x is well defined everywhere except when x is equal to 0, correct? Because 1 over 0 is undefined. Well, if columns of the matrix X are correlated with each other, this is equivalent to 1 over a 0 matrix, and this is not defined. So we need to make sure that assumption 4 holds for this math to hold. And in fact, for this math to hold as well. Assumption 4 is needed here as well. Now, we have two more properties. If assumptions 1, 2, 3, and 4 again are satisfied, then the OLS estimator is unbiased, which means that on average, my estimate is equal to the true value I am trying to find. So if you give me 10 different samples with the same sample size, I can compute 10 different beta hats, and I can take the average. It should get me closer to the true value. Since I only take the average of 10 samples, it won't be exactly equal to beta 0, but it should get me closer. Finally, the last one says that if assumptions 1, 2, 3, 4, and 5 are satisfied, then the OLS estimator has one more nice property. It is the best linear and biased estimator. So, among all estimators which are unbiased, there might be others. There are others. This one, the OLS one, will be the one with the lowest variance. This will be particularly useful once we get into hypothesis testing and inference. Any questions so far? There is a lot to ingest, I know, and to digest. So please take a look at it again online at home. You can take a look at it online, look at the textbooks. Those are the 4 fundamental properties of the OLS estimator. And it is important that you understand why each assumption is important and what role each plays for each property. Now, we obtained our beta hat OLS. Great, we can say a bunch of things. Now, how can we assess whether our estimate is a good estimate? After all, if the sample is equal to infinity, we are very close to the true value. But what if our sample is equal to 150? How close is it to the true value? You know, considerations like that. How can we judge the quality of a model? There are different measures, and for the linear model, in general we use the R squared. This is a formula you should remember. The R squared measures the percentage of variance explained by the model. So, you look at, this is pretty much the top of the ratio is the variance of the predictions, y hat being the prediction. Everything with a hat is an estimate or a prediction, divided by the actual variance of y, which is data minus average. Take the square to make a distance, and then finally, here we would take the expectation with 1 over n in front, but since both sides have a 1 over n, they cancel out. The result is exactly the same. So it is a ratio. It is a ratio of variances. So, it is a percentage, and it is always between 0 and 1. The closer it is to 1, the better the fit. This means that when it's close to 1, it means that the top is close to the bottom. So it means that the predictions, it means that the variance explained by the model is very close to the variance of the actual data. So it means that our model is able to fit the data pretty well, pretty accurately. Depending on the problem at hand, a R-square of 0.2 sometimes is acceptable. I've seen cases where the R-square is 0.1. In economics papers, at least more than 10 years old papers, R squared is equal to 0.2 was an acceptable number, 0.1 as well. But if you go to other fields of statistics, you might find that at least 0.7 is required to trust the results of a regression. It all depends on the sample size, the number of variables which are being used, and so on and so forth. Don't be afraid if you get the R square of 0.2. It is already something, honestly. However, if your R square is exactly equal to 1, it is not good either. You want to get high, but you don't want to get too high. This is what we call overfitting. If R square is equal to 1, it means that our prediction goes through every single point of the scatter plot. So we are able to, our predictions are exactly equal to the actual data. But the thing is, any model can predict the data used to estimate the model. You add more variables, and the R square will always mechanically increase. It's actually a mathematical result, even when the additional variables are irrelevant. So if you want to make your R square high, just add a bunch of variables, even some which supposedly have no impact on Y. That will make the R square increase. But it does not increase the quality of your predictions, because your predictions are coming from meaningless variables. But the other concern is, why would I care about predicting what I observe? If I observe the data, why do I need to predict it? A prediction is just a noisy estimate of a true value. If I observe the true value, I should just keep the true value. What's the point in predicting it? So models can always be better at predicting the sample it is actually estimating on. But if I already have access to this data, why do I care about predicting that data? What I want to predict is something which is out of the data. I want to use my model, my estimates, my beta hats, and apply them to a brand new data set and predict another data set. Predict a data set where I do not observe Y. For example, predicting the future. I have access to past data that I use to build my model, and then my model can be extended to, oh, what if the value of X tomorrow is equal to this? Then my prediction will be equal to that. So we need a way to test how well our model performs out of sample. In sample, we can always make it better. But the better it gets in sample, the worse it's going to be out of sample. Because the regression line is customized just for that particular sample. But if you put that regression line on any other sample, then it might get way off. It will be way more off. I will talk about this in the model selection lecture. I'll talk about why do we choose one variable over another? How do we choose one model versus another? And so on and so forth. Let's get to the last part before the illustration in R. Here I want to talk about inference and hypothesis testing. This section is going to be pretty short because this is not the point of the course, but I still need to tell you about it. You probably know about it already, so I need to refresh you about it, because I am talking about statistical models, and inference is a huge part of it. So, we use a sample to learn something about the true value of a parameter of interest. Great. Beta hat OLS is only an estimate of what we are interested about beta 0. It is not the true number. Hopefully it's close enough. Sometimes it's hard to know if it's close enough. But if you remember theorem 2, the asymptotic distribution, we saw that on the left hand side there is square root of n times beta hat OLS minus beta 0. So the true beta 0 is right there. So maybe we can play around with the math to say something about the true beta 0. This is what we call inference. Inference is the act of making a generalization based on one or a couple observations. If I was to make inference about the weather in Vancouver, I would say, oh, today it's gray and this morning it rained a bit. So maybe I can generalize that it rains on a regular basis in Vancouver. This is a generalization based on my observation. But if I came to Vancouver for the first time in the summer and I saw 30 degrees outside, I would say, wow, Vancouver is a hot city. That's just my conclusion, my generalization of that single observation. Hypothesis testing is a decision-making problem. Do we reject an hypothesis about beta 0 or do we not reject it? Remember, we don't know beta 0, we are just trying to learn things about it. Hypothesis testing is a way to learn something more about it. We make an hypothesis about what beta 0 could be equal to 0, could be equal to 200, I don't know, could be positive, could be negative. And then I use my test to tell whether I believe this to be true or not. We use a statistic, it's going to be a formula, to decide whether or not the data in the sample have been generated by the hypothesized population. So we make an hypothesis. If this hypothesis is correct, the data should have been distributed in a specific way. The sample should look like a certain feature. Under that feature, is it likely that my beta 0 is equal to my hypothesis or not? So here is the general procedure, and I'm being very vague here. First of all, you formulate a null hypothesis about beta 0, and we call this H0. The alternative hypothesis, H1, is either the complement of H0 or something which is not H0 but not necessarily the complement either. Then you decide on a confidence level. You cannot tell with a 100% confidence level that an hypothesis is true or not. There is always a margin for error. Since you want the margin for error to be small, in general, we choose a confidence level of 95%. So there is a 5% chance of rejecting the null hypothesis when the hypothesis is true. So we have a 5% chance of making a mistake, saying that something is wrong, whereas it in fact is right. Given this hypothesis, we will get a distribution or a statistic. You might remember the t-test. The t-test, it is something that works which is valid under H0. If you remember when you build your t-statistic, you replace beta 0 by whatever value in your hypothesis. This is because the hypothesis says, if this is true, then the corresponding t-statistic should be true as well and should follow a certain distribution. So we look at the statistic and we look at where it falls in the distribution it is supposed to follow. If what we observe is considered too rare, remember your t-stat is too high, higher than 1.96 in general, this is considered too rare. There's only a 5% chance that I observe something there, and I observe it in my sample. There's There's no way. There's no way that my hypothesis can be true then, because it's too rare. The fact that I observe it now means that it cannot be true. This is what we conclude. So if we consider it too rare, according to the confidence level, then we reject H0. So we say it's not possible that beta 0 is equal to that. We don't necessarily accept the alternative. We are just saying this for sure is not true. Anything else could be true, but that is not. That's what I believe. And then you can move on to another hypothesis test. Remember that often the procedure involves using the asymptotic distribution. We use theorem 2 in beta hat OLS to make inference about beta 0. But theorem 2 says that when the sample size goes to infinity, I get a normal distribution. In real life, my sample is not equal to infinity. It's equal to 1,000, 10,000, sometimes 100. So, how good of an approximation is the normal distribution in this case? Well, that's up for debate. Sometimes 100 is enough. Sometimes 100 is not enough at all, and you need at least 5,000. So, we use an approximation. We use the normal distribution as an approximation. So remember that when you conduct inference and make hypothesis tests, not only there is a margin for error just by the definition of a hypothesis test, but also to answer this question, reject or not reject, you use an approximation. So there is another margin for error coming from the approximation. It is hard to quantify, so always act with caution when you conduct inference. Don't be too categorical. Don't say it cannot be 0. It's I reject, my hypothesis tests reject, my procedure rejects that number, and then you can look at what could possibly go wrong. If you do not find anything that could go wrong, you say, okay, I am fairly confident in my decision. Any questions? I know I went pretty fast on this because I won't ask you to do too much about hypothesis tests. I might expect you to know how to interpret coefficients and make hypothesis tests if I show you regression results, but I will give you more information on that later on in the semester. But you should understand the general procedure, because as soon as you hear hypothesis testing, it doesn't have to be if you're looking at linear model, or if you're looking at estimating an average, estimating a proportion, or doing anything else. A hypothesis test always works the same way. Make the null. Under the null, there is a distribution or a statistic that should be true. Look at the distribution of this statistic. If the likelihood of observing this statistic is too rare, then you reject. This is too rare. It is too rare to observe this, and I am observing it now. So there's no way that this was the distribution it came from. So I reject. If not, it's like, oh yeah, that's possible. It's possible to observe that with a relatively high level of confidence. So I do not reject. Okay, let's get into the fun part. Let's illustrate all of that in Rstudio. So, quick word. R is the statistical software or the statistical language. Okay? So all these things that I wrote here are R commands and R syntax. Rstudio is the interface. It is a software you download to run R commands. You do not need Rstudio to use R. You can download R on its own and write your commands on R. It turns out that R doesn't look good. Like, the interface is hard to use, it's not convenient, and it doesn't produce a nice output. Rstudio is way nicer to use. And in fact, it's been made by the R community, by the creators of R. So, In this last 20 minutes, I'm going to go over a couple of regressions where I generated my own data. So I'm going to illustrate the different theorems I talked about previously using generated data. I will give you an introduction to R later. So for now, just follow what I'm saying, and maybe you can copy this code and paste it into your RStudio and run it at the same time as me. So to generate data, first of all, I need to generate a sample. So I need to know the sample size. This is what I call n. N, and this arrow could also be an equal. R doesn't mind equal or arrow. Means assign. So I'm going to assign the value 10 to n. So I make a very small sample size. Sample size of 10. That's not great, but that's a start. Then remember, my model is linear. I'm assuming it's linear, so I'm going to create a linear model. This means that I need an error term, and here I'm going to generate my error term epsi for epsilon in a normal distribution. And this is what R norm means. Random normal distribution. N inside means that I want n numbers, or n here is this n. So I want 10 numbers generated randomly from a normal distribution with a 0 average and a standard deviation of 1. So a standard normal distribution. I generate them independently because assumption 2 says my sample should be IID. After epsilon, now I need x. So I am building the right-hand side piece by piece, and once I have all the pieces, I'm going to put them together to create my y. So x is going to be my main explanatory variable, and it is also a randomly, like a normally distributed random variable, just because it's easy. Okay? Average of 0, standard deviation of 1. I can change that too if I want to. No big deal. Now, I need to attach the coefficients, the real betas. So beta 0 is the actual beta. In here, it is composed of two numbers. So C here stands for concatenate, because I am making a vector. It contains number 1 and number 2. 1 is going to be my intercept. It's going to be a bunch of 1s every time. And 2 is going to be the coefficient associated to x. So now if I want to create y, I need to multiply my coefficients by my variables. So what I'm going to do is I'm going to create a variable called, like a variable equal to 1, which is my intercept. And this one will be multiplied by the first number of beta 0, which is 1. And x here is going to be multiplied by the second number of beta 0, which is 2. This is what this notation is doing. cbind is creating a column of 1s and a column of my x's. I have 10 x's, and I'm going to have 10 1s. And this funky formula here is going to make this column vector a row vector to multiply by beta 0. And I get my combination plus my error term. So here, I know what the true coefficients are, because I am God. I am generating the data here. I am playing God. My true parameters are 1 and 2. And I want to see if I estimate 1 and 2, I want to see how close my estimates are going to be to the true numbers. So for this, I'm going to make a regression, and the command lm is going to do what I want. lm stands for linear model, and inside is what we call a formula. Every time you see a tilde in R, it's a formula. It says that I want to regress y on x and an intercept. By default, R here includes an intercept as well. If I want to remove the intercept, I have to put a -1, as if I wanted to remove this one here, or this one here. Now R, for the first one, the one called OLS, that's just the object, the name of the object, the name of what I want to make. You could put any other name here. Here I just put the name noInt for no intercept. So now R understands that it needs to make a regression of y on an intercept and x. So it's a univariate regression. So R will apply exactly the same formula as the one I showed you. The covariance between y and x over the variance of y. And same for the intercept. Let's see how it looks once I ask R to spit out the summary of my model. OLS is the name of my model from here. So when I say summary, this is what R is going to show me. So R first says, what did you ask for? I asked for this thing, and that's a formula. Then it's going to report quantiles on the residuals. The residuals, remember, are the difference between the data and the predictions. But what we are interested in are the coefficients. The intercept is estimated at 1.40. This is beta 0 hat. And the estimate on x is equal to 1.3. Remember, if I look at the previous code, the real coefficients are 1 and 2. My estimate is 1.4 when the true value is 1, and 1.3 when the true value is 2. Pardon my French, but that's pretty shitty, right? That's not very accurate. If I am making a regression like this for the government, I'm going to give pretty bad predictions, and the government might lose billions of dollars just by following my results to conduct policy or increase the tax or, and so on. The standard error is the estimated variance of beta hat. The t-value is the one you use for inference. It is the ratio between the estimate and the standard error. So if you do 1.4043 divided by 0.2786, you are going to get 5.040. Remember that those t-values are the ones you compare to the critical value of a student or normal distribution. And if they are too big, then we reject H0. And this is what the last one says. What is the probability of being higher than our t-value? It's a tiny probability. It is smaller than 5%. Because it is smaller than 5%, then we're going to have 2 stars. 2 stars Oh, it's even smaller than 0.01. So we have 2 stars there, yeah. This is the significance level. It means that if you make the hypothesis test for a 5% confidence level, or 95%, then you're going to reject the hypothesis that the true number is 0. Well, the true number is 1 and 2. In each of these results, we find that we would reject the hypothesis that each of those numbers are equal to 0. So at least our hypothesis tests are not wrong, but our estimates are not great. What do you think that is? Well, I have a sample size of 10 observations. That's not a lot. That's not a lot. The last 3 lines are a couple of statistics. There is only one of them I want to show you. That will be the multiple R squared. This is the formula I showed previously. And the R squared here is very, very big, 0.73. This is due to the fact in particular that I am fitting a straight line on 10 points. So it is relatively easy to go through 10 points. So the fit is actually pretty good. Also, I am putting the right variables into my regression. I am putting the right x. Imagine I put another y, another x that was totally irrelevant. Probably my R squared would be way lower. If I have no intercepts, everything is exactly the same, but now you can see that in my estimates, I don't have any intercept anymore. I only have the main coefficient. And in fact, it's pretty close to what I had before, 134.26 versus 131.06. Still a pretty shitty estimate. But the lack of precision comes from the fact that our sample is too small. So let's ramp it up. Let's increase the sample size. Let's put n to 1000 and nothing else changes. I just generate a bigger sample. My true values are 1 and 2. I run the exact same models as before. According to theorem 1, my estimates should be closer to 1 and 2, to the true values. Well, that's quite the case. 0.97 is pretty close to 1, and 1.96 pretty close to 2. The standard errors are very small as well, so that you can see the t-values are even bigger than before. Remember that the more stars you have, the more significant a variable is. Significance is when we test the hypothesis that the true coefficient is equal to 0. The more stars we have, the more we reject the hypothesis that the true coefficients are equal to 0. The R squared is still pretty good, 0.8, it's amazing. So you can see that now, by just increasing the sample size, my numbers are way closer to the true values. Here I have no intercept, only x, and 1.93 is also pretty close to 2. At home, I advise you to change that number and add another 0, or another 0, as many zeros as you want. Eventually R is going to have a hard time with the math, but you can put another 0 without any problem, and let me know if indeed the estimates are getting closer. They will. Now, I also said that the estimates were unbiased. The OLS estimates, the OLS coefficients were unbiased. To see this, let's fix the sample size to 100, but I'm going to generate many samples of 100, the same way every time. For each sample, I'm going to compute my OLS estimates. So I'm going to have 1 per sample, and then I'm going to take the average. If I have many samples, my average should be close to the true average. So here there is this variable called nsim, which is the number of rounds of simulation. So I'm going to create 1000 samples, and each sample has 100 observations. But each sample is created the exact same way. Again, 1 and 2 are the coefficients, the true coefficients. So what I'm going to do now is, I don't want to run this 1000 times, copy and paste. So I'm going to tell R to do this 1000 times automatically. This is what we call a loop. I'm going to get there once I give you an introduction to R. The idea is that I'm going to make an index called I, and it's going to start at 1. Then R is going to run this sequence of instructions, create the variables, put them together, and make a linear model, and collect the coefficients. Then it's going to go to the end here, the curly bracket, and R is going to say, my I is equal to 1, but my loop says it should go all the way to the number nsim, which is 1000. So now R is going to increase this number I by 1, and is going to start all over again, and say, now I is equal to 2. I'm going to generate another sample and run another OLS on it. And I'm going to keep the coefficients somewhere. And R is going to do this 1000 times. Then what I do at the end is I compute the average of all of my coefficients, which is what I call beta hat. And I find that my intercept on average, my estimated intercept on average, is equal to 1.00. Pretty good when the real number is 1. And my estimated slope is on average equal to 1.9978. Pretty close to 2. So what I'm doing here is I'm computing the average over samples of the same size. And my sample is not very big. But by taking the average over many, many samples, I can get close to the truth as well. I want to take maybe 3 more minutes to talk about binary explanatory variables. There should be 3 or 4 more slides. So, some covariates are qualitative. X sometimes is just not a continuum of numbers. It could be smoking status, yes or no, marital status, single versus married versus widowed, and so on. Ethnic status, there is black, Asian, white, Latino, or anything else. How do you relate those covariates to the dependent variable? Well, R, or any statistical software, does not really understand yes and no. They understand numbers. What you can do, however, is code a dummy variable. A dummy variable is a variable which is equal to either 0 or 1. So, a non-smoker could get a 0, and a smoker could get a 1. Every time you see smoker equals yes, you put a 1. So imagine that X is such a variable. The effect now is that X is either 1 or 0. So if you take the expectation of Y among smokers, so this is the average Y for which X is equal to 1, so the average Y among smokers minus the average Y among non-smokers, mathematically speaking, the expectation of epsilon will disappear every time. The beta zeros are going to cancel out. And you're going to end up with beta 1 times 1, in this case here. And in this case, beta 1 times 0, because X is equal to 0. So at the end of the day, when you take the difference between the two, you get beta 1. So beta 1 is the effect of being a smoker versus a non-smoker, fixing everything else. You could have the same age, same height, same weight, same income, same number of kids, but one of them is a smoker, the other isn't. So if there are other variables, the slope is totally unchanged. The dummy variable, however, will change the intercept. Because now, in this regression, when X is equal to 1, my regression is beta 0 plus beta 1. If X is equal to 0, my regression becomes beta 0. The difference between the two will be equal to beta 1. So beta 1 is going to either elevate or go lower than when X is equal to 0. So if I do this, if I do the same generating variables, imagine I have an X, which is continuous. I have a variable called smoker, which is either 1 or 0. I created it. And an intercept. Don't pay attention to the numbers. They are it's consistent, no problem. 3 stars. Very good R squared. We have 1,000 observations. No problem with that. What I want to show is that the estimate on the smoker variable is minus 5.11. It means that between a smoker and a non-smoker, whatever else they are, as long as everything is the same, age, number of kids, income, whatever other variable, the difference in Y between the two, between a smoker and a non-smoker, will be equal to minus 5.11. And this is what this graph is showing. This graph is showing 2 regression lines with the same slope, because those slopes are the estimated slope on X. For both groups, smokers and non-smokers, the slope is the same. It is the estimated slope on X, 2.96975. But for non-smokers, the regression line is higher because a smoker, when you're a smoker, the effect of being a smoker on Y is actually negative. So this minus 5.11 is the difference between this point and this point. Or this point and this point. So those two lines are parallel because they have the same slope on X, the estimated coefficient on X. The difference is in the intercept due to the fact that some are smokers and some are not. We will need to understand binary variables in particular in the 4th week once we get into causal inference methods. Finally, 2 more slides. What if the marginal effect is not constant? So think about the effect of age on earnings. Younger workers, if they work 1 extra year, tend to have a higher wage increase than older workers. So it means that age does not have the same effect on your wage depending on how old you are. So one way or another, we need to include the fact that older people, the effect of age on older workers is different from the effect of age on younger workers. So what we can do is add, for instance, a square term. So x could be age, and x squared is age squared. The model is still linear because it's linear in beta 0, beta 1, and beta 2. The marginal effect, however, if you take the derivative of y with respect to x, you get beta 1, a constant, plus 2 beta 2, a constant, times xi. But xi is not constant. It's a random variable. It depends on the age of people. So if beta 2 is negative, the older a person is, the lower the marginal effect. But if beta 2 is positive, the bigger the x, so the bigger the age, the older the worker, the higher the effect on earnings, on the wage. The reason I want to show you this is because if there is indeed a sort of non-linear relationship between age and earnings, like we see actually in the data, then if you run a linear regression, the dark blue line, you're going to miss the main effect. You can see that here, you're going through the middle, but there are no points here. And your prediction at 10 years of experience is pretty bad. Your prediction is here, whereas the actual data is down there, the orange points. Same here, in the middle. So by including a square term, the new regression line is able to capture the fact that when you're 25 years old, you have higher promotions than when you are 55 years old. So always be agnostic about your data and always ask yourself, could there be an effect which is not constant? A marginal effect which is not constant. Age and experience are such effects. Every time you deal with age data, include a square somewhere, chances are you're going to see an effect like that, where as you get, you're young, so you get high increase in your wage, but maybe eventually you reach 15 years of experience. It's like 45 years old or something. I don't know. I just made it up. And eventually you don't get that many promotions anymore because, well, you might be less dynamic, you might train less, you might have less skills than the new young workers, and so on. That's it for this review on linear models. Have a good rest of your week, and see you in the next one. Bye.